Hello friends, welcome to this lecture. So in this lecture we will continue our study of phase portrait of the linear system. So in previous lecture we have discussed two cases in which in both the cases we have assumed that eigenvalues are real, unequal and maybe of same sign or say opposite sign. So in this case we will just continue our study. So in this let us start with the third case. The third case is that roots are real but equal. So roots are real and equal. So now in that case let us have the following theorem. It says that if the roots of the characteristic equation of the system 1 are real and equal, then the steady state is again a node. So here this thing we have already. So in the case when it is real, unequal and of the same sign, then also it is node. Now in this case when we have real but it is not unequal, it is equal, then also it is a node. So let us see that how it is. So let us say that consider the lambda 1 and lambda 2 is equal to lambda, and let us assume that it is less than 0. So here we have two cases depending on a1 a2 a b c d. So first case is that a equal to d is non-zero and b equal to c equal to 0. Basically it is corresponding to the case, then we have a scalar matrix here. So it is a and d here, a diagonal matrix basically, right. Now in fact in this case a equal to d, so we can say that we have a scalar matrix, and the other case when it is not a scalar matrix. So let us do a proof one by one. So let us consider the case 1. In this case we assume that lambda 1 equal to lambda 2 and matrix is of this kind. So in this case your lambda is nothing but the value of a and d. So lambda is equal to a equal to d here. So we can write down that system is dx by dt equal to lambda x and dy by dt equal to lambda y. So in this case if you recall, your lambda 1 equal to lambda 2 and equal to, let us say, this quantity, one of this quantity a or d. So in this case when it is a scalar matrix, then in this case we are assuming that since it is scalar matrix, your u and v are two linearly independent exists because it is a diagonalizable matrix. So it means that in this case we must have two linearly independent eigenvector corresponding to lambda 1 equal to lambda 2 equal to lambda. Let us call this value as lambda. So in this case your system is reduced to this dx by dt equal to lambda x, dy by dt equal to lambda y, and corresponding to lambda we have two linearly independent eigenvector u and v here. Because we are assuming that linear system is since matrix A is a diagonalizable matrix because it is a scalar matrix, basically it is a diagonal matrix. So the general system will be solution is then x y equal to c1 e to power lambda t and c2 e to power lambda t, where c1 and c2 are arbitrary constant. In fact you can look at here, solution will be what, x y equal to c1 e to power lambda t u1 u2 plus c2 e to power lambda t v1 and v2. So if you look at here what I can write it here, x y equal to, now I can write it here e to power lambda t, you can take it out, then it is what, c1 u1 plus c2 v1 and c1 u2 plus c2 v2, right. And these are some, since c1 and c2 are arbitrary, so it will take arbitrary value. So we can write down this solution as x y equal to, so e to power lambda t, and here we have some constant c1 and c2 here. So c1 tilde, or you can call it, these are some arbitrary constants c1, since c1 and c2 are arbitrary constant. So this c1 tilde and c2 tilde are also arbitrary. Let us call this as c1 and c2 here. So it means that here c1 and c2 are arbitrary constant. Now this solution represent half lines of all possible slopes. If you look at the slope of this will be what, if you just for the time being let us forget this e to power lambda t, then this will represent what? X y equal to C1 tilde C2 tilde, and C1 tilde and C2 tilde are arbitrary. So, it means that the slope of this will be C2 tilde upon C1 tilde. Now, these are arbitrary, so slope are also arbitrary. So, it means that this represent the half line with the slope C2 tilde upon C1 tilde. Now, these are arbitrary, so it means that I can draw several half lines passing through origin, right, and your solution is tending to 0 because lambda is, we have assumed that lambda is less than 0. So, as t tending to infinity, solution will tend to 0 along the line with the slope C2 tilde upon C1 tilde. So, it means that your solution will tend to 0 along these lines here, right. So, it means that in this case your origin is a node because all the lines are approaching 0 comma 0 as well as entering 0 comma 0 along these lines. Okay. So, here 0 comma 0 is node and it is a stable node, basically it is asymptotically stable node, and in this case we call that 0 solution is node and asymptotically stable, and we also have a special name for this kind of phase portrait, and we call this, that this type of node is called a star shaped node because every solution is entering to 0 comma 0 along the half lines, right. So, these so solution will enter to origin along these half lines. Now, C1 and C2 are arbitrary, so these half lines are arbitrary. In final many half lines are towards origin 0 comma 0 here, right. And if lambda is greater than 0, then these path enter 0 comma 0 as t tending to minus infinity, or we can say that they move towards infinity as t tending to plus infinity along these half lines. So, in this case your half line will remain the same, the only thing is that solution is now moving away from origin, and in this case 0 comma 0 is a node but unstable node, and these kind of nodes are known as star shaped node. So, this is the case when your matrix are having equal roots and basically diagonalizable, that is the case we have considered. Now, look at example based on this. So, draw the phase portrait of the linear system y1 dash equal to y1, y2 dash equal to y2. The only critical point of the given linear system is 0 comma 0 because their determinant is coming out to be 1. So, it is non-zero. So, 0 comma 0 is the only critical point, and we can find out the eigenvalue of this. In fact, it is an identity matrix. So, eigenvalues are nothing but 1 comma 1, and you can check that eigenvectors are 1 0 and 0 1 corresponding to lambda equal to lambda 1 equal to lambda 2 equal to 1. So, here your eigenvalues are real, equal and positive. So, critical point 0 comma 0 is node and it is unstable. Is it okay? Now, your phase portrait will be like this. So, you draw several lines and along these lines it is moving away from origin. So, you can draw several lines because constants are arbitrary. So, it is a star shaped node. Now, proof of case B. So, in this case lambda is negative, let us assume that it is negative, double root excluding the circumstances of case 1. Now, case A basically correspond to the case in which roots are equal, but the eigenvectors are say enough linearly independent, n linearly independent eigenvectors are there. So, it means that the case 1 is basically correspond to the case where the matrix is diagonalizable. Now, this case when matrix is not diagonalizable, it means that we are not having enough number of linearly independent eigenvectors, then what to do? So, in this case lambda is lambda 1 equal to lambda 2, let us assume that it is negative, but it is we are not able to get your enough number of linearly independent eigenvectors. So, in this case your general solution is given by x equal to C1 a e to power lambda t plus C2 a1 t plus a2 t e to power lambda t, y equal to C1 b e to power lambda t plus C2 b1 t plus b2 e to power lambda t. So, let me write down your solution will be what, xy e to power lambda t, your u plus e to power lambda t, let us call this C1 and C2 here. Here we have I plus a minus lambda I t, and here we have say v here. So, if you simplify this, it is what, C1 e to power lambda t, it is u1 u2 plus C2 e to power lambda t, you can take it out, this is 1 0 0 1 plus this is some matrix something and t, and this is v1 and v2. So, when you simplify you will get this kind of form, right. So, xy is given by this. Now, not only this, please observe that these ABs are constants and C1 and C2 are arbitrary constant, and we have this thing B1 upon A1 equal to B by A. So, how we can get this? If you look at this, that basically we if you recall how we are obtaining this B, V here, V is called as generalized eigenvector, and we obtain this V as the solution of something that A minus lambda I square V is 0, but it is A minus lambda I square V equal to 0, but A minus lambda I V is non-zero. Okay. So, we have obtained like this. So, if you look at, I can write this as A minus lambda I operating on A minus lambda I V equal to 0. So, if you look at this A minus lambda I V, if you call this as W, then this W is an eigenvector corresponding to the lambda. Now, we already have that U is an eigenvector corresponding to lambda. So, it means that W must be written as some constant multiple of U. So, it means that W, if I am writing as W is basically this A minus lambda I into this. So, W is basically, if I look at here, W is basically given as A1 and B1. So, here it is W1. So, it is W1. Now, sorry, W here. Now, U is basically your A and B. So, if you look at this W is a constant multiple of U. So, it means that W is constant multiple of U. It means that this A1 is equal to K times A and B1 is equal to K times of B here, where K is some non-zero. So, it means that we can easily verify that B1 upon A1 is equal to B upon A here. Now, here again we have two possible cases. Let us say that choosing C2 equal to 0 and C1 equal. So, if you choose C2 equal to 0, then this part is gone and we have xy equal to C1 a e to power lambda t, C1 b e to power lambda t. So, corresponding to this we have your solution will be xy equal to C1 e to power lambda t, and here we have simply u, that is A and B here, right. So, here AB is just a constant. So, we can simply this simply represent a line passing through origin with the slope B by A. So, these are lines here. Now, as lambda is negative, so solution is tending to 0 comma 0 here, right. Now, as for any C1 greater than 0, the solution 10 represent a path consisting of half of the line Bx equal to Ay, this is the line Bx equal to Ay of slope B comma A, and for any C1 less than 0, they represent the path consisting the other half of this line. Now, since lambda is less than 0, both of these half line path approach and enter 0 comma 0 with the slope B by A as t tending to infinity, that we have pointed out here, that this is the line having slope B by A, and since lambda is negative, so as t tending to infinity, xy both is tending to 0 0 along the line having the slope B by A. Okay. Now, what happen if C2 is non-zero? So, in this case the general solution represent non-rectilinear paths, and these rectilinear paths also approach and enter 0 comma 0 as t tending to plus infinity, and with the same limiting slope. Just look at here, the solution is this. and so let us look at the slope here. So, slope will be what? Y upon x. So, y upon x will be what? E to the power lambda t, you can take it out. So, we will get C1 b plus C2, and here we have B1 t plus B2, and here we have C1a plus C2 A1 t plus A2. Now, and if we divide it by t here, right. So, what you will get? So, I will get here C1 b by t, here C1 a by t plus C2 b2 divided by t, here also C2 a2 divided by t plus C2 b1, and here it is C2 a1. So, these term will simply vanish. The only thing will left is that b1 upon a1. So, limit of, so what you get, limit t tending to infinity y by x is equal to b1 by a1. So, it is b1 by a1, which is same as writing b by a here, right. So, it means that the earlier line along with your solution is tending to origin. So, it means that this simply says that even the non-rectilinear path are also entering 0 comma 0 along the same line which we have just drawn. So, it means that ultimately your solution are moving towards origin along the line this. Is it okay? So, here in this case your all the solutions are entering 0 comma 0 along the line given by this, which is the line containing the eigenvector corresponding to the eigenvector corresponding to lambda 1 equal to lambda here. So, it means that here we have only one eigenvector, and solution will tend to 0 comma 0 along the half line given by this eigenvector here. So, in this case all the paths both rectilinear and non rectilinear enter 0 comma 0 as t tending to plus infinity with slope b comma a, and hence the critical point origin is node and asymptotically stable. Now, the other case when lambda is positive, that the same result will be obtained except that the fixed point is unstable in this case. So, in this case your fixed point is unstable. So, just for say phase portrait of this, let us consider the following thing. You have xy dash equal to 1 1 0 1 xy. So, here eigenvalues lambda 1 equal to lambda 2 equal to 1, let us okay. So, here eigenvalues are same. Now, corresponding to eigenvector, if you find out the eigenvector corresponding to lambda 1 equal to lambda 2 equal to lambda equal to 1, it is 0 1 0 0. So, and v1 and v2. So, solution will be that v2 is equal to 0. So, your solution eigenvector will get only this 1 comma 0. So, there is no other linearly independent eigenvector available. So, in this case you have to find out the other eigenvectors, means generalized eigenvector, which is a solution of a minus lambda I square u equal to 0. So, if you look at a minus lambda, lambda is 1 here. So, it is 0 1 0 0 whole square, it means 0 1 0 0 and u equal to 0. So, if it is nothing but 0 matrix u1 and u2. So, you can say that your this will give you what? This will give you that u1 and u2 may be any of choice. So, we will choose the eigenvector which is linearly independent of the earlier one. So, it is, let us say that 0 1 is your generalized eigenvector. So, solution will be written as xy equal to say C1 e to the power t, and eigenvector is 1 0 plus C2 your e to the power t, and here we have I, that is 1 0 0 1 plus t times a minus lambda I, that is 0 1 0 0, and here it is 0 1. So, we simplify C1 e to the power t 1 0 plus C2 e to the power t you can still write, and if you multiply you will get 0 1, and here if you multiply you will get 1 0 and t, right. So, here it is if you recall, recall this case here. So, here if you look at A and B will be what? So, here you can say we want to verify this B1 upon A1 equal to B upon A. So, that we can verify here. So, this is A and B and this is your A1 B1 sorry, what is this? It is A1 B1, okay. So, it is A1 B1 and this is A2 B2. No, A1 it corresponding to T. So, here this is A2 B2 and this is A1 B1 because it is corresponding to. So, we can easily see that here A and B and A1 B1 are same, exactly same. So, of course, ratio will be same, slope will be same, B1 upon A1 is same as B upon A here, is it okay? So, in this case it is 0. So, in fact, these are coming out to be same here, okay. So, all the solution in this case will so eigenvector is 1 0. So, 1 0 means 1 and 0. So, 1 0 is a point here, x is equal to 1 and y is equal to 0. So, it means that all these are solution will tend to 0 and any other will tend to 0. So, your phase portrait will be like this, okay. So, now consider the next case, theorem 4, and it is corresponding the case when eigenvalues are complex and it is not purely imaginary. So, it means that if the roots of the characteristic equation of the system 1 are conjugate complex with non-zero real part, then the fixed point is a spiral point. So, let us have the proof of this. So, let lambda 1 and lambda 2 be given by alpha plus I beta and alpha minus I beta, and none of them is 0. So, since we are assuming that it is complex, so beta is non-zero, and we are also assuming that it has non-zero real part, it means that alpha is also non-zero. Then the general solution of the system 1 may be written as this: x equal to e to power alpha t and so on, this one. So, here how we can obtain this? If you recall, your solution will be what? X y equal to e to power alpha plus I beta t and u1 plus I u2, right, and when you simplify you will get this, right. So, it means that this I am leaving it to you, that please verify that your solution is given by equation number 11 here. So, here ai's and bi's are different definite constant and C1 and C2 are arbitrary constant. So, definite constant means your A1 B1 is coming from this and another one A1 A2 B2 is given by this. So, it means that let alpha is less than 0. Now, let us assume that since alpha is non-zero, so it may be positive, it may be negative. So, let us consider that alpha is less than 0. So, let alpha is less than 0, then from 11 we see that the solution tends to origin as t tending to infinity. So, as alpha tending to infinity, as alpha is negative, t tending to infinity means this term is tending to 0, similarly this term also. So, x y is tending to 0 0 as t tending to infinity. Now, we can rewrite our solution x and y in this following format: x y as e to power alpha t c3 cos of beta t plus c4 sin of beta t, and y as e to power alpha t c5 cos of beta t plus c6 sin of beta t, and where c3 c4 c5 c6 can be given as the earliest c1 c2 and a1 a1 a2 b1 b2, we can write it like that. This is not very difficult. You rearrange and you simply arrange the coefficient of cos of beta t and sin of beta t, you will get this. Now, again we can rewrite this in a very compact form, and it is given by this: x equal to k1 e to power alpha t cos of beta t plus phi 1, and y as k2 e to power alpha t cos of beta t plus phi 2. Now, here this is using geometric, here k1 is given by under root c3 square plus c4 square, and k2 is given by under root c5 square plus c6 square, and phi 1 and phi 2 are defined by the equation this, that cos of phi 1 is c3 upon k1, cos of phi 2 equal to c5 upon k2, sin of phi 1 equal to minus c4 upon k1, and so on. So, it means that I am assuming that you can rewrite equation number 11 as equation number 13 here. So, this is the more compact form and we start working with this. Now idea is to say that here, since t tending to infinity, your x and y both component will tend to will approach to 0 comma 0. Now we want to know that what is the limiting slope. If limiting slope is finite, we call that origin as node. If they are approaching but not entering 0 comma 0, then the origin is known as the spiral point or focal point. So here let us find out the slope here. Slope is y by x, k2 upon k2 e to power alpha t cos of beta t plus phi 2, k1 e to power alpha t cos of beta t plus phi 1. Now and this phi 2 and phi 1, since if c1 and c2 are arbitrary, then this phi 2 and phi 1 may not be the same thing. So here by simple rearrangement, let us assume that k equal to k2 upon k1 and phi 3 as phi 1 minus phi 2, and assuming that phi 1 and phi 2 since c1 and c2 are arbitrary, so phi 3 is not ideally equal to 0 here. So y by x we can rewrite like this. So k cos of beta t plus phi 2 I am replacing as phi 1 minus phi 3. So we are writing and cos of beta t plus phi 1. Now here we can simply simplify this using this as a minus. So cos of a minus b you can apply, and it is written as k cos of beta t plus phi 1 cos of phi 3 plus sine of this thing divided by this, or we can rewrite this thing. The idea is that if you take the limit here, then this is independent of t, this is independent of t, this will depend on t. So as t tending to infinity, tan of beta t plus phi 1 will tend to infinity. So it means that limit does not exist, right. So we simply say that limit t tending to infinity y by x is not a finite quantity. So it means that this in this case origin is not a node here, right. So though we know that 0 comma 0 is stable but not a node, and why you can understand why we are doing all this thing. We can do it here also, but the thing is that here we simply say that here these will cancel out. So k2 upon k1, this may be equal if phi 2 and phi 1 are equal. So here we simply say that limit t tending to infinity, limit does not exist. So that is why we did this kind of say arrangement. So here what we have concluded here, now since the limit of y by x does not exist as t tending to infinity, the path do not enter 0 comma 0, but it follows from the previous equation that the path approaches origin in a spiral like manner. So it means that it is tending to 0 comma 0, but it is not taking any say a slope. So it means that there is no finite slope. So it means that there is a possibility that it will approach to origin in a spiral like manner, winding origin in an infinite number of times as t tending to infinity. Thus the critical point is a spiral point, and also it is asymptotically stable as alpha is less than 0, and if alpha is greater than 0, then situation will reverse. It means that it will be spiral but not a stable one, it will be unstable spiral, and here we simply say that origin is unstable spiral. Now here we can conclude the same thing from this. Here if you look at this, what you will get here. So we can write x equal to k1 e to power alpha t cos of beta t plus phi 1, y equal to k2 e to power alpha t cos of beta t plus phi 2. So here we in place of writing cos of beta t plus phi 1, we can again simplify, and from here also we can get that it is basically kind of a periodic. If you look at here, it is periodic of 2 pi by beta, right. So x is periodic with period 2 pi by beta, and y is also periodic with period 2 pi by beta here. Is it okay? So here if I replace t by t plus 2 pi by beta, so what you will get? You will get x of t plus 2 pi by beta will be k1 e to power alpha t plus alpha 2 pi by beta, and cos of beta t. So beta t will be beta t, and here beta will be cancelled, it is 2 pi. So beta t plus phi 1 plus 2 pi. So it is nothing but same. So it means that it will be coming out to the same thing. The only thing is that now radius is changed. It is not e to power alpha t anymore. Now it is e to power alpha. So it will be like I can write it x of t plus 2 pi by beta equal to x into e to the power 2 pi alpha by beta, right. So, here we have assumed that alpha is negative, and let us say that beta is something. So, here we can say that here your radius is changing, right. So, here we simply say that I am assuming right now that beta is positive here. So, we simply say that the distance is reduced from the earlier one, right. So, here we simply say that it is tending to 0 comma 0 with a small with say radius lesser than the earlier one. So, it means that it is basically it is something like this, oh sorry ulta, just opposite or this way. So, again there are two possibilities, whether it will follow this or it will follow this, it depend on I think it is same, sorry it is like this. So, it is the this thing side, okay. So, here there are two possibilities. Now, let us consider one example. So, this it will follow which path, that will depend on the equation itself. Now, let us look at this example, example 4. Draw the phase portrait for the linear system y1 dash equal to y1 plus y2, y2 dash equal to minus y1 plus y2, and we want to look at the behavior of origin, that is 0 comma 0, and we can check that origin is the only critical point of the given linear system, that is because the determinant is non-zero. And look at the eigenvalues here. So, eigenvalues is coming out to be lambda 1 equal to 1 plus I and lambda 2 equal to 1 minus I. So, eigenvalues are complex conjugate to each other with positive and real positive real part. So, in this case 0 comma 0 is the spiral point, but it is unstable spiral point, and we want to find out the phase portrait in this case. So, here there are two possibilities, that the solution will move like this or solution will move. So, which one it will follow, whether it is going the anti-clockwise or it is moving the clockwise, it is anti-clockwise here. So, which path it will follow. So, for that choose a point on some, so let us say choose this point, right. Similarly here, so let us say this is y1 here and this is y2 here, this is y1 here and y2 here. So, at this particular point your y2 is 0 and y1 is positive. So, and here if you look at above this y2 is positive and below this y2 is negative. So, basically we want to look at the behavior of y2 at this particular point. So, to look at the behavior of y2, look at the second equation, differential equation in terms of y2. So, here y2 dash is equal to minus y1 plus y2. So, at this particular point, your y1 is positive, so this is negative, y2 is equal to 0. So, this is simply, so at this point your y2 dash is equal to minus y1. So, y1 is positive, so y2 is negative, y2 dash is negative. So, it means that y2 is decreasing. So, it means that your y2 is coming from positive to negative side, because it is y2 is 0 here and here it is decreasing. So, it means that y2 is going to negative side rather than positive side. So, it means that it will follow this path only rather than this path, because here at this particular point your direction is this way, direction is this way. So, here at this particular point your y2 is moving from negative side to positive side. It means that here y2 dash has to be positive, but from the equation it is coming out that y2 dash is negative. So, it means that this is not the correct phase portrait, this is the correct phase portrait. Okay, so, here we have seen that both the eigenvalues are complex conjugate with this positive real part. The critical point 0 comma 0 of the given system is unstable spiral point here. So, with this we will finish our lecture here. So, in this lecture what we have discussed two cases. One is when eigenvalues are real but equal. In that case we have shown that that origin is node, but whether it is star shaped or say it is only simply a node, that will depend on the eigenvectors corresponding to the eigenvalues lambda. And other case we have considered is that when lambda 1 lambda 2 are complex conjugate to each other, and we have non-zero real part. In this case we have shown that it is a spiral point. Now whether it is stable or unstable, that will depend on the real part of the eigenvalue lambda. So if real part of the eigenvalues are positive, then it is unstable. If real part of the eigenvalue is negative, then it is a stable spiral point. So in next class we will consider one more case, and we will discuss some more properties. So with this we will conclude, and thank you very much for listening us. Thank you.